Howdy doody. We recently saw the fundamental theorem of calculus, which gives us two connections between integrals and antiderivatives. But one thing that we're lacking is convenient notation for working with antiderivatives. We had been using capital letters for antiderivatives. If our function was lowercase f of x, then capital F of x meant the antiderivative. But if we want to say that we're doing an antiderivative, we have to write out the whole sentence, take the antiderivative of this, blah, blah, blah. And it just ends up being messy. And also, there are situations where we want to be able to deal with capital letters that aren't antiderivatives. So it's really not that convenient to work that way. And so, because of the connection between antiderivatives and integrals, there was a notation that was created that looks like an integral, and it's to refer to the antiderivative of a function. And so basically, if we want to take the antiderivative of a function, we're going to put an integral symbol in front of it, but we're not going to write in limits of integration, and we'll put a dx to mean that we're taking the antiderivative with respect to x. And so this notation, where we have the integral symbol without limits, basically refers to the fact that we're going to take the antiderivative. And there's a name for this, and this is basically an indefinite integral. So this notation gives us capital F of x, and this means that capital F prime of x equals lowercase f of x. Basically, if we ever have notation like this, it means we want the antiderivative of the function on the inside. So, for example, if we wanted to take the antiderivative of x cubed, we could write it like this, and we know that the antiderivative of x cubed is x to the fourth over 4 plus a constant. So we are good to go. And in general, instead of saying antiderivatives moving forwards, we will say we are going to take the integral of x cubed. And if we don't have limits, that is an indefinite integral. And if there are limits of integration written, that is a definite integral. And it's very important to understand the difference between these things. When we have an indefinite integral, the results that we get is going to be a function or a family of functions, because there's that ambiguous constant term. If we were to take a definite integral, for example, the integral from 0 to 2 of x cubed dx, this is going to end up giving us a number. In fact, we write x to the fourth over 4, and we evaluate that at 0 and 2 and take the difference. So that's going to be 2 to the fourth over 4 minus 0 to the fourth over 4. 2 to the fourth is 16. 16 over 4 minus 0 is just 4. And so when we take a definite integral, the result that we end up getting is a number. And when we have an indefinite integral, the result that we end up with is a family of functions. It's super important to understand that difference. And the relationship between these things is that when we are taking a definite integral from the fundamental theorem of calculus part 2, we look at that indefinite integral, or the antiderivative, we evaluate it at the limits, we take the difference, and that is our answer. There is a very simple way to write the relationship between a definite integral and an indefinite integral, and it looks like this. If we want the definite integral from a to b of f of x dx, we can take that indefinite integral and we can evaluate it at b and a and take the difference. Now, the effectiveness of the fundamental theorem of calculus for integrating things for us depends on having a supply of antiderivatives of functions, because if we don't have an antiderivative of a function, we can't integrate. And so let's remind ourselves of some of the most common antiderivatives that we'll work with. All right. In the very top, we have some properties of, and instead of saying antiderivatives, I'm just going to start calling these indefinite integrals. So we've got some properties of indefinite integrals. If we're taking the integral of a constant times a function, we can pull the constant outside and multiply it by the integral of the function. And if we have a sum of two functions that we're integrating, we can integrate them separately and take the sum. And then if we are integrating a constant, that integral is just the constant times x plus the constant of integration. But then below are the kind of the fundamental ones that we're looking at. So this first one is the power rule. If you're integrating a power function x to the n, you get x to the n plus 1 over n plus 1 plus c. Basically, you raise the exponent by 1 and then divide by the result. The integral of e to the x is just e to the x plus c. The integral of sine of x is negative cosine of x plus c. Secant squared gives us tangent. Secant tangent gives us secant. Those are some of the trig ones. There's a nice inverse trig one. The integral of 1 over x squared plus 1 dx is equal to inverse tangent of x plus a constant. You'll remember that the integral of 1 over x is ln of the absolute value of x plus a constant. There is a similar version of a to the x instead of e to the x. When we integrate that, we get a to the x over ln of a plus a constant. And then there's some more trig ones down here. The integral of cosine is sine. The integral of cosecant squared is negative cotangent. The integral of cosecant cotangent is negative cosecant. And then the integral of 1 over the square root of 1 minus x squared is inverse sine. These trigonometric ones come from our knowledge of derivatives of trigonometric functions. Now, I'd like to do a couple of examples, but we are running out of space, so I'm going to do those in the next video.